During the 2014 EV Tech Expo and Battery Show, EC Power held a contest called the AutoLion Battery Safety Challenge. The problem statement read as follows. A 5 amp hour pouch cell with dimensions of 130 by 80 by 5 millimeters has an NCM graphite chemistry with 120 watt-hours per kilogram energy density. This cell undergoes a nail penetration test at 100% stated charge under room temperature conditions with a 20 millimeter diameter nail, 10 millimeter, and 5 millimeter diameter nail. If it takes 150 seconds to reach 150 degrees Celsius with a 20 millimeter nail, and it takes 75 seconds to reach 150 degrees Celsius with the 10 millimeter nail, how long will it take to reach the same temperature with the 5 millimeter nail? Now, out of all the hundreds of responses we got, most entries attempted some sort of linear extrapolation, with the vast majority of answers being around 37.5 seconds. This makes intuitive sense if you base your response on the time it takes for the other two nail diameters to reach 150 degrees. So based on the simulation results shown here, we can see that the larger nail diameters reach 150 degrees in what appears to be a linear descending trend. But now if we add the results from the 5 millimeter nail, we can see that the results clearly depart from the linear trend, with the cell reaching 150 degrees Celsius within 2 seconds of penetration. So what's really going on here? How can this behavior be explained? The key here lies in the interplay between the electrochemical, geometric, and thermal effects during the short. Upon nail penetration, there's a large inrush current within the first few seconds, after which the current is regulated by the internal resistance of the battery. This inrush current generates substantial I2R heating in the nail. The smaller diameter nail has a smaller thermal mass and less ability to reject heat axially, which leads to the highly concentrated local heating, which results in the development of dangerous conditions within the first few seconds of penetration. The larger nail, however, with greater thermal mass and ability to reject heat axially, can withstand the inrush current without reaching dangerous conditions. This results in heating which is global in nature and has a much longer time scale. This problem highlights the importance of using a physics-based software such as AutoLion, which captures the electrochemical, thermal, and geometric factors of nail penetration that determine safety for a given cell. Simulating such an event using software that simplifies or neglects any of these aspects will result in failure to capture both local and global heating and will not give accurate results. So, out of the 464 total entries, about 80% of the responses guessed between 35 and 40 seconds. There were only 7 entries that guessed between 0 and 10 seconds, but nobody guessed the correct answer. Given these results and how close they were, we decided to pull the closest 7 answers and draw a random entry to win the iPad. The entry we drew was Charmaine Whitting of Next Tier Automotive. So congratulations, Charmaine. We'll be contacting you shortly about the prize. To everyone else that submitted an entry, we thank you for taking the time to fill out a form and stopping by our booth to see what AutoLion was all about. Hopefully we'll see you all next year.